This question asks specifically about unpaired electrons for each of the elements in ground state. The only way that we can tackle this problem is to draw orbital diagrams. Now we don't need to draw the complete orbital diagram, just the one for the final sublevel. The sublevel that would be filled would house the last electron. So let's take a look at each of these elements. First, I have sulfur. Sulfur's ground state configuration ends with 3p4. In any p sublevel, you have 3 orbitals in it. And if they're saying that there are 4 electrons housed in this p sublevel, and I start drawing arrows, as is typical for orbital diagrams, we have, in this case, 2 unpaired electrons. Electrons that are not in an orbital with another electron. This orbital has 2 electrons, so those are paired up, but the other 2 orbitals are not. The next element is tungsten. Tungsten, once you look it up on the periodic table and see where it is, you'll see that it has a ground state configuration that ends with 5d4. Well, any d sublevel has 5 orbitals in it. So if we draw, and they're telling us we have 4 electrons in it, draw arrows to represent those 4 electrons. All 4 are unpaired. So we have 4 unpaired electrons for tungsten. Chlorine has a ground state configuration that ends with 3p5. All p sublevels have 3 orbitals in them. I'm going to draw arrows to represent the 5 electrons in the 3p sublevel for chlorine. Only one of the boxes has an unpaired arrow. That's the one unpaired electron that chlorine contains. Zirconium has a ground state configuration that ends with 4d2. So I'm going to draw a set of boxes that represents the 4d sublevel. Notice that there are 5 boxes in that sublevel, as is the case with any d sublevel. I'll draw 2 arrows to represent the 2 electrons found in that sublevel for zirconium. And both of those electrons are housed in separate orbitals and therefore are unpaired. So there are 2 unpaired electrons in zirconium at ground state. Oxygen has a ground state configuration that ends with 2p4. I'll draw 3 boxes to represent that p sublevel, and I'll draw 4 arrows to represent those 4 electrons. 2 of the 3 boxes have unpaired electrons, so there are 2 unpaired electrons in oxygen. Rhodium ends with 4d7 in its ground state configuration. And if we draw a series of 5 boxes to represent that d sublevel, and in it we draw 7 arrows following off-bow principle and Pauli exclusion principle and Hund's rule, of the 5 boxes, 3 of them contain unpaired electrons, and thus rhodium has 3 unpaired electrons. Niobium has a configuration that ends with 4d3. I'll draw 3 arrows to represent the 3 electrons in that d sublevel, all of which are unpaired. So we have 3 unpaired electrons. And then the last one, this is a fun one. we have oxygen with a +1 charge. That's pretty rare. Remember, oxygen is one of the most electronegative elements out there. So for it to have a +1 charge, it probably bonded with fluorine, the only element that's more electronegative than oxygen. So anyway, if it has a +1 charge, that means there's one more proton than electron. And if any and all oxygen atoms have 8 protons, that means we have a total of 7 electrons in that atom. Okay, 7 electrons. That sounds like something that ends with 2p3. In other words, this atom has the same electron configuration as nitrogen, the element that precedes oxygen on the periodic table. Okay, so p sublevel, we've got 3 electrons in it, 1, 2, 3, and all 3 of them are unpaired. And so we have 3 unpaired electrons.